Hello bachon, let's read the question. So the question says, in Young's double slit experiment, monochromatic light of wavelength 630 nanometer illuminates a pair of slits and produces an interference pattern in which two consecutive bright fringes are separated by 8.1 mm. Another source of monochromatic light produces the interference pattern in which two consecutive bright fringes are separated by 7.2 mm. Find the wavelength of the light from the second source. And the second thing it asks us is, what is the effect on the interference fringes if the monochromatic source is replaced by a source of white light? So, to understand the question, we must first revise the key concept behind this question. So, the key concepts behind this question is Young's double slit experiment. So, in Young's double slit experiment, when two slits which were small d distance apart were placed and an incoming wavefront, primary wavefront came, and due to the slits are very small, the slits are kept very small, and hence interference is observed. Due to interference, the and superposition of the secondary wavefronts, when we place a screen distance capital D apart, this is our screen, then there is a bright central white spot observed, and then there are white spots at regular intervals. Okay, so this was observed in Young's double slit experiment, and the distance between each white spot is called beta, which is uh, fringe width, which is being asked in our question. So let us revise the formula for fringe width. So fringe width beta is given by lambda into capital D over small d. Here lambda is the wavelength of incoming light, d is the distance between slits and screen, small d is the distance between two slits. Now let us jump right into our solution. We have everything prerequisite for our solution. So for solution part, we have beta 1 is equal to lambda 1 capital D1. Sorry, in this case, D1 and small d, D and small d are kept constant because the aperture is not changing, and hence lambda 1 d over small d, and then beta 2 comes out to be equal to lambda 2 d over small d. Now we find beta 1 over beta 2 from the above equation. We get lambda 1 over lambda 2. From here we have, as we have beta 1 is given to us as 8.1 millimeter, 8.1 into 10 to the power minus 3 meters. Beta 2 is given to us as 7.2 millimeter, 7.2 into 10 to the power minus 3 meter. Lambda 1 is given to us as 690 meter, which means 630 it is. It is 630 meters, 630 nanometer. So 630 into 10 to the power minus 9 meters. We have to find lambda 2. So from this equation, when we put our values, we get 8.1 into 10 to the power minus 3 over 7.2 into 10 to the power minus 3 is equal to 630 into 10 to the power minus 9 upon lambda 2. From here, when we solve it, we get 0.9 cancels this by 8 times and this by 9 times. 9 cancels it by 70 times, and hence lambda 2 comes out to be equal to 70 into 10 to the power minus 9 into 8, which then formulates to be 560 into 10 to the power minus 9 meters. This is in meter, and hence it is 560 nanometer. So this is the wavelength of second light being used, and let's highlight it here. This is our final answer. I hope you understood it well. Thank you.